Hey guys, today we're gonna do section 5.6, which is gonna focus on solving equations. So we're gonna have exponential equations, and we're gonna solve them. Now, the only problem with this is there's kind of different ways to solve based on the situation you're in and the problem you're given. Okay, so like one way, if there is one base with one exponent, all you need to do is isolate the base, so get the base by itself, like we've kind of got here, and rewrite it as a logarithm. And then once you have that, you should be able to solve it. If both sides contain exponents, so like over here, I've got a base to a power equals a base to a power, that's going to be a completely different situation. And for that, we're going to take the log of both sides. We're going to take the log of this side, the log of this side, and we're going to rewrite both sides using our power rule, where if you take the log of a power, you can write it as a product, and then I won't have any exponents to worry about. This exponent is now a factor, and I can solve it using a different method. Okay, so first off, let me show you these first few. These first few are pretty straightforward. If you have a base to a power, just rewrite it as a logarithm. So x equals log base 3 of 7. And now that we've got a situation like this with a log base 3, which we don't have on our calculator, but we can use that change of base formula, so the log of 7 over the log of 3. So put that in your calculator. Log 7 divided by log 3, and 1.771. That looks pretty good. X equals 1.771. So that's it. That's your answer. Okay. For B, B looks similar, but our base is not isolated. Okay, we've got this 5 that's multiplying our base. So that's just the first thing we need to do. We need to get rid of that 5. So we're just going to divide both sides by 5 like you would just an Algebra 1 problem. That'll leave us with 2x. And then 3 divided by 5, 3/5, that's like 0.6. But now I've got a base to a power equals a value. So x equals log base 2 of 0.6. I can plug that in my calculator as the log of 0.6 divided by the log of 2. All right, I'm going to get x equals negative, and then 0.737. 0.737. All right, the next one looks a lot different because the variable looks different, but it's going to be handled the same way. You've got a base to a power equals a value. So let's rewrite this as a logarithm. So 3x minus 1 equals log base 2 of 32. It's the same setup. We're going to figure out what this equals, and then we're just going to solve this. This will be like a two-step equation after that. Okay, so log base 2 of 32. Now, you could put that in your calculator. You may just recognize that 32 would be a multiple of 2. So, 2 cubed is 8. 2 to the 4th is 16th. So 2 to the 5th would be 32. So log base 2 of 32 is 5. If you didn't just know that, and you plugged it in your calculator, it would tell you that the answer is 5. Okay, then we can add 1, divide by 3, and there you go. So the first step was kind of a pre-calculus step, but then after that, it was just Algebra 1. Okay? All right. These last two. Now, these are a little trickier. Okay? So prepare yourself. All right. So I've got a base to a power equals a base to a power. So I can't just rewrite this as a log or rewrite this side as a log because I'm still going to have a power that I have to deal with. So instead, what we do is we're going to take the log of both sides. So I'm just going to take just the log, just the common log. So the log of 5 to the x minus 2, and then I'm going to take the log of 3 to the 3x. As long as you do the same thing to both sides, everything's fair. Now, what I can do is, I've got these exponents. I really don't want exponents. I want everything to be on one level playing field so I can access it and I can solve for it. So we're going to use that rule that says the log of a base to a power equals the product of that power and the log. So we're going to take this x minus 2 and we're going to bring it out front. We did this the last section. So x minus 2 log of 5 equals, and then the same thing here, 3x log of 3. Now, this is now an algebra problem that I can solve. I'm trying to solve for x. Now I've got an x over here and I got an x over here. The first thing I'm going to do is I'm going to distribute right here. I'm going to take this log of 5 and I'm going to distribute it into my parentheses. So it's going to be x log of 5 minus 2 log of 5 equals, and then there's nothing to simplify right now, 3x log of 3. Alright, so that's my problem. Now, remember what we're trying to do. We're trying to solve for x. I've got an x there, and I've got an x there. We've done this before when we were doing inverses. The idea is we want to get the x's together, and then I'll be able to factor that x out, and then I'll just have one x. Okay, so that's the trick. So I've got an x here, I've got an x here, and then this does not have an x. So what I'm going to do is I'm going to move my x's to the left. I'm going to move this guy this way, and I'm going to move this that doesn't have an x, I'm going to move him that way. Okay, so I'll have x log of 5. I'm bringing, this guy's positive, I'm bringing him over, so he's going to be minus 3x log of 3 equals, and then this was a minus 2, so it's going to come over here and become a positive 2 log 5. And then I've got the x's together, so I can factor them out, leaving us with log 5 minus 3 log 3 equals 2 log 5. And then, well, I've got 2 more steps. My x is multiplying all this, so I need to divide by all that. X equals 2 log 5 divided by log 5 minus 3 log 3. Now there's a lot going on here, and I know that. Okay, and I got to keep track of all this as I'm going step by step by step. Right now it's just a calculator problem. So now my job is to clear this. So I'm going to put parentheses just in case. So parentheses 2 log. Now I use the common log, so I can just use my common log button. 5 parentheses divided by parentheses, and then it's going to be log 5 minus 3 log 3, close my parentheses. Don't feel good about what I just did. Okay, I need a set of parentheses here. So I'm going to insert the parentheses. I need to close that log. This closed that log, but then I want to close my entire parentheses. That should be good. Okay, equals, and I get negative 1 point, what was it, 90, we'll say 9. Alright, now that is solving an equation. Okay, we just did a lot of things right there. So, we're going to try to do it again. Okay, so, I'll go a little faster this time because we've all seen this happen. So, same thing. I'm going to take the log of both sides. Log of 2 to the x minus 1 and the log of 5 to the 2x plus 3. If you think that you could do this, then you could pause the video and try to do this on your own and then watch my steps and see if they follow yours. Okay? Now that I've taken the log of both sides, I'm going to bring my exponent out front. So I'm going to use that power rule. X minus 1 log of 2, and then 2x plus 3 log of 5. I am now going to distribute. I'm going to open up these parentheses. So the log of 2 is going to multiply both of this. So x log of 2 minus, and then it'll just be log of 2. I'm going to distribute over here. So that'll be 2x log of 5 plus 3 log of 5. Alright, I've got an x here, I've got an x here. I'm going to get those guys together. X log 2 minus 2x log 5. I'm going to take this minus log, I'm going to bring him to the other side. I want my non-x's to be on the same side. Now I can factor out that x. And then I'm going to divide by this. So x equals, and then it's going to be log 2 plus 3 log 5, and then over log 2 minus 2 log 5. All right. So now it's calculator. X equals, let's see what we got here. Clear. So it's going to be log, all right, maybe I want to start with parentheses. Log 2, close parentheses, plus 3 log 5, close parentheses, and then close the parentheses that I started with, divided by parentheses, log 2, close the parentheses, minus 2 log 5, close the parentheses, and then close the original parentheses. Alright, now I'm going to hope I hit everything right. I'm kind of backtracking, making sure. Yep, I just wanted to check on my work before I hit equals, and x equals negative 2.186. Alright, and that's that. Now, there's another way to solve equations. And that has to do if you have similar bases. So if you have bases on both sides, but if the bases are the same, okay? So for example, this right here, this is example C from the top. If we would have noticed right off the bat that 32 is 2 to the 5th power, if you have the same base, then the only way these two things can be equal is if the exponents equal each other as well. So if you have the same base, you can just ignore the bases and just set the exponents equal, and that's your entire problem. 3x equals 6, x equals 2, you're done. That's the problem. Okay, over here, I've got a 3 and I have a 27. But 27 is 3 to the 3rd power. So if I think of 27 is 3 to the 3rd, now I have the same base. And the only way that they can be equal is if the exponents equal each other. So you can just set the exponents equal. X squared minus 7 equals, now over here I have a power to a power. So those are multiplying. So that's 6x. But that's it. Now I have a quadratic. I can solve this. X squared minus 6x minus 7 equals 0. Factors of negative 7 that add up to negative 6 will be minus 7 and plus 1. So x equals positive 7 or negative 1. There's two solutions on that one. That's it. Okay? C, same thing. E to the 2x minus 1 equals, now I have two e's that are multiplying each other. If you're multiplying a base, you add the exponents. So I can simplify this and combine these into one term. Negative 3x and negative 4x would be negative 7x. And now I have the same base being taken to a power, so I can set them equal. And that's it. This is now an algebra problem. I'm going to subtract 2x to the other side, divide by negative 9. I'm just going to leave my answer like that. That's perfect. Okay? Don't put it in your calculator. Just leave it. Okay? Last one. Try this one. Negative x squared equals, I'm going to combine these. Now, they're not like terms, so the only thing I can do is I can add them together. Negative 3 plus 2x, just leave it like that. But that's good. Okay, I've got the same base. I can set the exponents equal to each other. I've got a quadratic. I'm going to put them on the same side. X squared plus 2x minus 3. Factors of negative 3 that add up to positive 2 are going to be plus 3 and minus 1. So x equals negative 3 and 1, and those are my solutions. Okay, so take a look at, oh, nope, now we've got another side to do. All right. All right, so now that we know how to solve some exponential equations, I want to recall some of the word problems and the formulas we looked at earlier, and to show how we could solve these for the exponents, which we haven't done yet. Okay, so when we looked at the compound interest or the continuous compounding formula, we were always given a certain amount of money, or maybe trying to figure out how much money we would start with to end up with a certain amount. But these, now we're going to be able to do things a little differently. So if you look at this example, how long will it take? So we're trying to figure out an amount of time. Well, time is our exponent up here, or up here, okay, depending on the problem. So we're going to be solving for one of our exponents. So how long will it take an initial investment of $10,000 to grow, so this is our initial amount, to grow to $25,000, so now that's our future amount, with a rate of 6% compounded continuously. So we're going to be using this formula. So 25,000 equals 10,000, and then e to the 0.06 t. All right, so the rules from the previous page said if we've got a base to a power, we need to isolate the base. So right now it's being multiplied by a 10,000. So we need to divide both sides by 10,000. So 25,000 times 10,000, well, 25 times divided by 10 is going to be 2.5, and then e to the 0.06 t. Now, I've got a base to a power equals a value. So I can rewrite this as a logarithm. This is a base e, so this is going to be a natural log. So 0.06t is equal to the natural log of 2.5. Once we've got this is now a calculator problem. We're just going to take the natural log of 2.5. So let me clear this out. Natural log 2.5 equals, okay, and then we're going to divide that by the 0.06 that's multiplying our t to get the t by itself. So we're going to divide by 0.06, and I get 15. We'll say 3. So 15.3 equals t. So the problem was, how long will it take an investment of 10,000 to turn into 25,000? Well, it's going to take over 15 years for that to happen. That money would just have to sit there. Okay? Look at the next one. 1,000 is invested at 8% compounded monthly. How long before you have 1,500? So we're going to end up, now I did not give a lot of space here. I'm going to start over here. I may have to do kind of 2 columns. So 1,500 equals, we're starting with 1,000. Now, this is compounded monthly, so this will be this formula. So 1 plus 0.08 divided by monthly is 12 to the 12t power. Okay, so we need to simplify this. I'm going to do 2 things. First off, we've got a base to a power. I don't really know what that base is, so we need to simplify that and figure out exactly what's going on in these parentheses. But we also need to get the base by itself. So I'm going to divide by this 1,000. So I'm going to divide by 1,000. So that's going to be 1.5 equals. Let's figure out what our base is. So clear. So 1 plus 0.08 divided by 12 is 1.00. I know I'm writing down a lot of things right here. Looks looks like it's 6 repeating to the 12t power. All right. So to solve this is now a base to a power equals a value. I need to write this as a logarithm. The base of my logarithm will be the base of this exponential over here. So it's going to be the log base 1.006 repeating, that's my base, of 1.5 equals 12t. All right, so this, yes, I get it. That is a very, very odd base, but we've got the change of base formula that will do this for us. So I'm going to come over here now, 12t is equal to the log of 1.5. So log of 1.5, and then divided by the log of 1.00, and then it was just a bunch of sixes. So I'm going to get 61 point, what was that? 0.223. And then we're going to divide by 12. So divide by 12. And I get 5 let's call that 5.09. So t is 5.09. So it'll take you about 5 years to turn $1,000 into $1,500 at that interest rate. Okay, so those are some money problems. Let's take a look at the growth and decay problems that we looked at earlier. So this is the same problem we had earlier. We have a colony of bacteria growing at a certain rate. Okay, how long will it take for the population to reach 140 grams? So this is our initial amount, 90. We want to know how long before our future amount is 140. So 140 equals 90 e to the 0.05 t. So just like what we did with the money, we're going to divide by 90. So 140 divided by 90. So what looks like 1.5 repeating equals e to the 0.05 t. This is an e, a natural number, so we're going to take the natural log of the other side. So the natural log of 1.5 repeating equals 0.05 t. So I've got two steps. I'm going to do the natural log of this, which is in my calculator. So I can do the natural log, and then I can hit the answer button. And then we're going to divide by the 0.05, and that's our answer. So t equals 8.8. I think this is in days. So it'll take 8.8 days to go from 90 to 140. Okay? B says, what is the doubling time? Well, for doubling, if we have 90, it just means when are we going to have 180? So everything else is the same setup. Now, first thing I have to do is isolate my base. So I'm going to divide. Well, 180 divided by 90 is 2. That's not a coincidence. This is a doubling time, so this is what should happen. So 2 equals e to the 0.05 t. So we are going to take the natural log of 2. And then we're going to divide that by 0.05. So calculator, natural log of 2, parentheses, don't forget the parentheses there, divided by 0.05, and 13.9, we'll say. T equals 13.9 days. That's how long it'll take to double. Okay? Now, we've got one more problem. This one's a little tougher. Okay? It has to do with half-life. So the half-life, so we've got some radioactive material. The half-life of radium is 1,690 years. So this is T. This is the amount of time that it takes this stuff to shrink down to half its original amount. If 10 grams are present now, how much will be present in 50 years? Well, we've got a problem here. We know what the half-life is, but we don't know actually what the decay rate. We need K. We don't know how fast this stuff is like shrinking. We just know that it takes 1,690 years to go from its original amount down to half. So this is actually a two-part problem. It just doesn't look like it. Okay, you see one question mark, you're being asked one question, you don't realize it's a two-parter. The first thing we have to do is figure out the decay rate. So the half-life is 1,690 years. So using this formula, the amount that I start with, okay, that's what this is. I'm going to start with a certain amount. I am going to end up with half of that amount. That's what a half-life would be. Whatever I start with, I'm going to have half of that over a certain amount of time. E to the, and then I've got a K and a T. Well, the K is what I'm trying to solve for. I'm trying to figure out what that K is. How fast or how slow is this stuff decaying? And the amount of time that it takes to get half of our amount is 1,690 1,690. Now, I need to solve this. First thing we're going to do is we're going to notice that these two A's are going to cancel each other out. I've got an A on this side and an A on this side. If I divide both sides by A, they're going to cancel, and I'm going to have 1/2 E, and then I'm going to flip these around so it looks more normal to us, where we have the number first followed by the variable. That's it. Okay, I just need to do this, and this is now a calculator problem. Take the natural log of 1/2, divide it by 1,690, and that'll be our K value. So, natural log of 1/2 equals, and then divide it by 1,690, and I get negative 0.000. All right, I'm gonna put 41. Okay, after that there was another 0, so I'm kind of running out of like significant digits. Okay, you could write all those down if you wanted. Okay, but I'm going to write that down. So now we know our K, we know our decay rate. So now this problem over here is pretty easy. Okay, we've got 10 grams present now, so how much will be present in 50 years? So we want to know the amount that we're going to have in 50 years. This is function notation. This isn't something I'm going to solve and divide by 50 or anything. This is just a function notation. Over here, it's going to be my initial amount, which is 10, my E to the negative 0.00041 power times my time, and in this case it's a 50. So I just need to plug all that in my calculator, and that's my answer. The amount that I will have in 50 years is 10 E to the negative 0.00041 times 50, 9.797, we'll say 9.8. Okay, this stuff does not decay very fast. Okay, it takes 1,690 years to go from 10 grams to 5 grams, because that'd be a half amount. Okay, so in a mere 50 years, this stuff is not going to shrink down very much, so 9.8. So that's it. So take a look at your worksheet and let me know if you have any questions on solving the equations or on these word problems. All right, thanks.